All right, everybody, welcome to the video here for lesson number 3 on geometric sequences. So in lesson 2, we learned about arithmetic sequences, which always have a common difference, meaning you can add the same value consistently throughout the pattern to get to the next value. Geometric sequences are a little bit differently. So since we can develop these a little bit differently, let's take a moment here and try the opening exercise. See if you can figure out the next couple numbers in this pattern. So go ahead, pause the video and see if you come up with the next few numbers. All right, so welcome back. Hopefully you tried this. So we have the first 3 terms of the sequence. So the 4th term of the sequence I'm going to get by doubling 24 or multiplying by 2. So that would make 24. The 5th term of the sequence would be multiply 24 by 2 or doubling it. That would make 48. And then the 6th term of the sequence, this would be 96. So in today's lesson, we're going to focus on writing the explicit formulas based on multiplying a value. So unlike lesson 2 where we consistently added a value, here we're going to consistently multiply a value. So I'm going to ask a very similar question to what we did in lesson 2. So assuming that we have a sub 1 is 3, how many times do we have to multiply 2 to get all the way to a sub 5? So a sub 5 was 48. So what I'm asking is, starting at 3, how many times do I have to multiply 2 to get the 48? So if I do it once, I have 6. If I do it twice, I have 12. 3 times, I would get 24. And one more time, I would make this true. So what we can say here is the term a sub 5 is equal to 3 times 2 to the 4th power. Notice the term we're trying to find and the exponent we're using are one apart from each other. So if we use this same idea to find a sub 10, we would start by saying 3 times 2 to the 9th power. Now, if we did that, it's going to be a relatively large number because we have an exponential thing happening here. So we have 1,536. The next term I'm asking you to find is the 23rd term. I wouldn't be able to have you find the 2020th term like we did yesterday. It'd be too big of a number. So if we found a sub 23, we can say 3 times 2, but to the exponent of 22. Now, if I type that into my calculator, I'm going to get a relatively large number. So we'll have 1, 2, 5, 8, 2, 9, 1, 2. So we have 12,582,912. Big number, but we're just understanding the concept here. So if we take this and look at it, we can say, all right, so we have this explicit formula now. So what would be the explicit formula for this sequence? So we said 3 is the starting number. That never changed. We always multiplied by 2. But then to find the exponent, it always was 1 less than whatever the term was you were trying to find. So if we want to find the nth term, 1 less than that would be n minus 1. So just like yesterday, there's a formula that can generate any explicit equation for a geometric sequence. That's what we're dealing with today. So a geometric sequence is a sequence where there's a common multiplier or common ratio is what we call it. The common ratio we call R. So the common ratio is a number that we're multiplying from one term to get to the next. To find the common ratio, you can divide the second term by the first term. That will always work if you notice that it's a geometric pattern. For example, in this last problem, the common ratio was 2. So if I was to take the second term and divide by the first term, I would get 2. So I can get that. Even though you can see that pattern, right? Some of them are not so obvious to see, which you'll start to see here. So number 2 gives us another ratio and asks us to write the explicit formula. To write the explicit formula, just like the one we did in lesson 2, we need to know the first term and the common ratio. First job we have to figure out is how do we find the common ratio? So what we can see here is to get from one term to the next, we're multiplying by a half. If you can't see that visually, just say, well, the common ratio is the second term divided by the first term. So the common ratio is 1/2. So any term of this sequence is going to be the first term times that common ratio to the n minus 1. Hey, look at that. We have our answer. So let's try a couple. So here's what I'm going to ask you to do. I'm going to ask you to try the first two here by yourself. Very simple, straightforward ones, just like the two examples we've already done. So pause the video and try the first two here, the two on top. So this 2, 10, 50 and the 5, 15, 45. See if you get the same answer as me. All right, great. So hopefully you tried these on your own. We noticed that the common ratio for this first one was 5. I'm going to multiply by 5 each time. And then the explicit formula is going to be 2 times 5 to the n minus 1. For the second one, I'm hoping you notice it was a multiplier of 3. So we said the common ratio is 3, and the explicit formula then becomes 5 times 3 to the n minus 1. Go ahead, try the next two. They're a little bit more challenging. Same idea, though. Pause the video and try them and see what you get. All right, so let's see how we did here. So for that first one, it's kind of tough to see. If you got 1/3 using mental math, good for you. If you didn't, I would say divide the second term by the first term. You get that 1/3. So you could say the explicit formula is going to be 108 times 1/3 to the n minus 1. The second one, same thing. If you saw that it was 1/7 just by using mental math, good for you. If you didn't, just divide the second and first term. So we could say any term of this sequence is 49 times 1/7 all to the n minus 1. All right, pause the video one more time and try the last two. All right, welcome back. The first one here is tough. I'm going to guess most of you did not get how to get from one term to the next using mental math. If you did and you got 2.5 or 5/2, however you did it, good for you. Give yourself a pat on the back. That one was tough. But I'm assuming most of us had to go through and say, all right, the second term is 2, the first term is 8. So if I divide that, I get 5/2 or 2.5, however you did it is fine. So then we can say a sub n is equal to the first term times 5/2 all to the n minus 1. For the second one, notice that this pattern goes positive, negative, positive, negative. This only happens in geometric sequences. This cannot happen in an arithmetic sequence because a common difference has to be the same addition or subtraction every single time. You're not going to ever be able to alternate between a positive and a negative. Here, if we make the common ratio a negative number, when you multiply a negative times a negative, it becomes a positive, but then if you multiply a negative again, it goes back to negative. So it's going to keep alternating between positives and negatives. And we'll see that this common ratio is in fact negative, because when I divide this out, I get -2. So now we could say any term of this sequence is equal to the first term times -2, all to the n minus 1. All right, so we've gone through here so far in this lesson and just kind of developed the idea of how we can use a geometric sequence. Now let's talk about the tougher questions, the questions that are asking us to do a little bit more. Right? Up until this point, we've basically just reviewed what you did in Algebra 1. Now let's jack it up a little bit here and give us an Algebra 2 type question. So here's number 4. So it says, consider the geometric sequence with a sub 2 value of 40. So we know the second term of the sequence is 40. And an a sub 5 value of 1080. So that means I don't know a sub 3. I don't know a sub 4. But I do know a sub 5 is 1080. I also don't know a sub 1. So to be able to figure out how we can determine the common ratio, I could do a couple different things. I could guess and check. I could say 40 times 2, that makes 80, times 2 makes 160, times 2 makes whatever that comes out to be. It's not 1080. And you can keep guessing and checking until you get to the answer. Or we could approach this a little bit more intelligently. So because this is a common multiplier, to undo multiplication, we use division. So if I take the fifth term, 1080, and divide it by 40, I get 27. So that means I would multiply 40 by 27 to get to 1080. Well, I want to figure out what number do I multiply 3 times to get there. So what number multiplies by itself 3 times to make 27? So essentially what I'm asking you to do is to take the cubed root of 27. So I'm figuring out what number multiplies by itself 3 times to make 27, and that answer is 3. Now, if you're not 100% positive if you did this right, you could always check it. 40 times 3 is 120. 120 times 3 is 360, and 360 times 3 makes 1080. So we wind up having the right value here. The next thing we have to do is figure out what the first term is. So if we're going from the second to third term by multiplying by 3 to work backwards, I would have to divide by 3. 40 divided by 3 is not a nice number, so we'll just leave it as 40 over 3. If you type that in the calculator, you're going to get 13.3 repeating. We don't like that, so we'll just leave it as a fraction. So now that I know the common ratio is 3, I know the first term is 40 over 3. I can say the explicit formula here is 40 over 3 times 3 to the n minus 1. We're just using what we know about multiplication to figure out what that common ratio is. Just like in lesson 2, we use what we knew about subtraction and addition to figure out what the common difference was. Number 5 says, what is the 15th term of the sequence? So we have this sequence that goes from positive to negative. One of the things that we should be able to identify right away is what type of number is the 15th term going to be. So like if we were in class, I would ask you the question. I'd say, look at the pattern and tell me, is the 15th term going to be positive or negative? And explain why. I'd give you a couple minutes to think about it, and then I'd hope that you'd all notice that all of the odd terms are positive, all of the even terms are negative. Since 15 is an odd number, it's going to be a positive answer. So if we go through, we can figure out, well, any term of the sequence, the explicit formula is 5 times negative 2 to the n minus 1. So if I want to find the 15th term of the sequence, I would say 5 times negative 2 to the 15 minus 1. If I plug that into my calculator, I wind up getting 81,920. Notice it's positive. If I asked you to find the 16th term, it would be a negative number and it would be a little bit bigger than that one. All right, let's take a look at a question that's similar to questions that we did back in that exponent and even the log unit. So it says a laboratory culture begins with 1,000 bacteria at the beginning of an experiment, which we denote by the time of 0 hours. By 2 hours, there are 2,080 bacteria. If the number of bacteria is increasing by a common factor each hour. So that term or that sentence is telling you that we're talking about a sequence. We're not talking about an exponential function. An exponential function is going to take into consideration every single second and minute that's happening and how much it's increasing at that time. This is saying that it's increasing at a common factor every single hour. So every hour it's going to go up by a number, not every minute or second, etc. And it wants us to figure out how many bacteria there are at 1 hour and at 3 hours. So let's take a look at what we know. We know that the initial amount is 1,000. We don't know how much there is at 1 hour, but we do know how much there is at 2 hours. There's 2,890. So just like we did in exercise 5, I'm going to divide the bigger number by the smaller number here, and we're going to get 2.89. Now that was what I multiplied to get from the first term to the second term, or third term in this case. I want to do some number multiplied by itself twice, right? So what do I multiply by itself twice to get 2.89? Well, to do that, I would say, well, take the square root of 2.89. Right? Square root is what multiplies by itself twice to get to that value. If I do that, I get 1.7. So my common ratio is 1.7. If you're not sure, check it. So if you do 1,000 times 1.7, you get 1,700. If you do 1700 times 1.7, you're going to get 2890. So we now know the first term. Let's find the third term. So we can multiply again by 1.7. If we do that, I get 4913. If you really want to, you could have come up with an equation for the explicit formula and do all of that, but just keep multiplying and that's good enough. It then says find the explicit formula for P sub n, where P sub 0 represents 0 hours. This is different. Because they're using 0 as the first number, the exponent of the explicit formula's got to change. So when we write the explicit formula here for P sub n, we're still going to start with, well, what do we start with? 1,000. We're still going to say the common ratio, but now we're just going to put an exponent of n. If we put n minus 1, when you plug in 0, you're going to get a negative value for n. I can't have that, right? I have to have an exponent that's always going to be a 0 or a higher. You can't have a negative number. So whenever the first term starts with 0, the exponent is always going to just be n. It's not going to be n minus 1. If the sequence starts with a sub 1, then the exponent in the explicit formula is going to be n minus 1. Hopefully this video helped explain things throughout the lesson. Pause it and then move on to the next page and try your homework assignment. See if you can figure out those questions without me, and then go back and rewatch to the second part of this video, and hopefully you got all the answers right. So I'll pause the video here for a minute. You pause the video, try your homework, and come back to the video and see how you did. All right, so hopefully you tried your homework here, and let's see how you did. So for the first one, I figured out that the first term was 5, and the common ratio was 2, and the explicit formula was 5 times 2 to the n minus 1. For the second one, we see that the first term is 8. The common ratio, now for this common ratio, if you didn't see it, you could always divide the second number by the first number and you get that 1/4. If you use 0.25, it's okay too. So then the explicit formula here would be 8 times 1/4 to the n minus 1. The next one, the first term is 100. The common ratio is -1/10. Again, if you didn't see that, just divide the second number by the first number. And the explicit formula winds up being 100 times -1/10 to the n minus 1. All right, now in number 2, I'm asking you to identify the sequences that are different. Right now we know 2 different types of sequences, so we have to identify which one is which so that you know when to do what. Right, so one of the things that you're going to have to be able to do after this lesson is be able to look at a sequence and say, oh, that's arithmetic, so I can do this, this, and this with it, or that's geometric, I can do that, that, and that with it, because there's different things that we learn in these first couple lessons. So looking at this first one, we notice that the difference here between each one is the same. So this is an arithmetic sequence. The common explicit formula is going to be the first term plus the common difference, which is 12, times n minus 1. This is from lesson 2. The second one we can identify as geometric right away because it alternates from positive to negative, but also because there's a common multiplier, right? We could see it's growing exponentially. So this is geometric. And the explicit formula here is going to be 6 times -3 to the n minus 1. All right, let's take a look at number 3. Number 3 says that every year Tony receives a 3% increase in his annual salary. His starting salary was $40,000. Does a geometric or arithmetic sequence best model Tony's salary? So the answer to this question is geometric, because the salary is increasing exponentially. Right? It's not going up by the same exact amount every single time. It's being multiplied by a value. All right. Since we want to increase by 3%, the common ratio is 1.03. That's what I'm going to multiply every single year to his previous year's salary to get his new salary. So if we want to write an explicit formula for Tony's salary, we would say T sub n is equal to his initial salary of $40,000 times 1.03, that's the common ratio. But now we have to think about the exponent. If T sub 1 was the first year, we'd make the exponent n minus 1, but they want T sub 0. So that's going to make our exponent just n. This way, when I plug in 0 for that first year, it's going to give me 40,000. Let's take a look at number 4. Number 4 asks us to find the common ratio for this geometric sequence. It gives us the second term, the fourth term, and the fifth term. To find any common ratio, all we have to do is divide a term and its previous term. Now I know 4 and 5 are next to each other. So the common ratio here would be whatever a sub 5 is divided by a sub 4. We don't actually even need a sub 2 at all. So we could go through and say, okay, the common ratio is negative 6.44204 divided by 5.8564. So the common ratio is negative 1.1. That's it. Now, if you didn't see that and you did a lot more work, like you found out what the fourth term divided by the second term was, and then you took the square root of that, you're going to get the same ratio, but this was way easier. Hopefully this video helped, and hopefully you're continuing to watch everything and keeping track with everything in class. Hopefully I see you soon, and best of luck with your homework.